Inside Samsung's 100-inch TV, how massive screens are built. Using 15B technology. One documentary narration script. Right now, somewhere in the world, a truck is delivering a single sheet of glass worth more than your car. It's flawless, perfectly flat, and it's about to become something you'll stare at for the next 10 years of your life. This is the inside story of how a 100-inch television is born. Not assembled, born. Because what happens inside these walls isn't manufacturing. It's closer to surgery. Let's start with something most people never think about. Before a single pixel can glow, before a single color can bleed across that massive screen in your living room, it all begins with sand. Refined, purified, melted, and drawn into sheets of glass so precise that the variation across its entire surface is less than the width of a human hair. These substrates arrive in sealed cassettes, transported under conditions more controlled than most hospital operating rooms. Temperature regulated, humidity locked, vibration dampened. Because a single fingerprint, a single particle of dust smaller than what your eye can see, would destroy everything. The factory you're looking at right now cost $15 billion to build. Not million, billion. And the air inside it is 10,000 times cleaner than the air outside. Every surface is stainless steel. Every floor is anti-static. Every person inside wears a full clean room suit, gloves, shoe covers, a mask, safety glasses. Not because of danger, because of dust. In this world, dust is the enemy. Dust is the thing that turns a $6,000 television into scrap. The moment that glass enters the production line, it will not be touched by a human hand for weeks. Robots handle everything. Air cushions float the glass from station to station so gently that the substrate never actually makes contact with the solid surface. It rides on a thin layer of pressurized air, hovering like a ghost through a cathedral of machines. First comes inspection. Automated cameras scan every square millimeter of that glass surface, searching for defects invisible to the naked eye. Micro scratches, inclusions, surface contamination at the molecular level. If a flaw is found, the sheet is rejected. There is no second chance. There is no repair. In this process, perfection isn't a goal. It's the minimum requirement. Then the glass is washed, not with tap water, with ultra-pure deionized water that's been filtered and processed until it contains almost nothing but H2O molecules. Soft sponge rollers turn against the surface. Ultrasonic waves shake loose any remaining particles, and then precision air knives blast the water away in a single smooth wave, leaving the glass not just clean, but surgically sterile. Now here's where things get wild. This is the part that justifies that $15 billion price tag. Inside sealed vacuum chambers, the glass enters a world with less air pressure than outer space. Magnetron sputtering systems fire atoms of metal onto the surface, one layer at a time. We're talking about building electronic circuits not by placing components, but by growing them, atom by atom, layer by layer. Thin film transistors materialize on the glass like frost forming on a winter window, except every crystal, every molecule, every connection is precisely controlled. Photolithography machines, some of the most complex devices ever built by human hands, project microscopic circuit patterns onto the glass using ultraviolet light. The resolution is staggering. Millions of individual transistors, each one smaller than a red blood cell, are patterned across a surface larger than a king-size bed. Think about that for a second. Millions of components too small to see, spread across a sheet of glass you could lie down on, and every single one has to work. After the circuits are etched and cleaned, the real magic begins. This is OLED deposition, and it's the reason this television will produce colors you've never seen before on any screen. Inside enormous vacuum chambers, organic compounds are heated in crucibles until they vaporize. These molecules rise like invisible smoke and settle onto the glass in layers measured in nanometers. A nanometer is 1/1000th of a meter. For reference, your fingernail grows about 1 nanometer per second. These layers are being deposited with that level of precision across a surface the size of a dining table in a process that cannot tolerate even the slightest contamination. Red, green, blue. 3 organic compounds, 3 colors of light, billions of self-emitting pixels that don't need a backlight. that produce their own illumination from within. That's why OLED blacks are absolute. When a pixel is off, it produces zero light. Not almost zero. Zero. True darkness. The kind of black that makes everything else on screen look like it's floating in space. But organic materials are fragile. Moisture and oxygen would destroy them in hours. So immediately after deposition, the panel enters an encapsulation chamber, where alternating layers of inorganic barrier film are deposited over the organics. Think of it as sealing a painting inside an invisible glass case, except the case is only a few hundred nanometers thick, and it has to last a decade. The panel is cured, the adhesives and barrier layers are stabilized under controlled heat, and then comes the cut. The mother glass, that enormous substrate that entered the line, now carries multiple television panels on its surface. A laser scribes a line across the glass with absolute precision, and then a mechanical bar applies pressure from below, and the glass separates along that line with a clean, quiet snap. 100 inches of future television liberated from the sheet that created it. Edge polishing smooths the cut. Another washing cycle removes every particle. And then the panel moves to a phase that bridges the microscopic world and the world you can hold in your hands. Driver IC bonding. Tiny chips on flexible film tapes are bonded to the panel edges using heat and pressure. These chips will translate digital signals into the voltages that control each individual pixel. Flexible cables are connected. A thermal management layer is applied to the back of the panel to dissipate heat. And for the first time, this sheet of glass starts to look like something you'd recognize. A precision-machined aluminum frame arrives, matte black anodized, engineered with tolerances measured in fractions of a millimeter. The OLED panel is lifted by a vacuum robot, tilted vertical, and lowered into the frame. Alignment pins guide it into position. Silicone gaskets cushion the glass edges. Screws are torqued to exact specifications. The panel and the frame become one. Now the electronics. A power supply board loaded with capacitors and transformers. A main board dense with processors, memory, and connectivity chips. Each board is placed onto standoff posts, screwed down, and connected with ribbon cables that click into zero insertion force connectors with a precision that's almost musical. Internal cables are routed through molded channels, clipped into place, checked and rechecked. A rear cover seals everything inside. And then, for the first time, the television is powered on. In a darkened calibration chamber, the screen illuminates, pure white. A colorimeter robot arm extends toward the surface and begins measuring luminance across every zone of that 100-inch display. Then gradients, then pure red, pure green, pure blue. Each color is measured against reference standards and adjusted until the television reproduces reality with scientific accuracy. This isn't a quality check, this is tuning an instrument. Dead pixel inspection follows. The screen goes pure black and an automated camera scans every inch, searching for any pixel that fails to stay dark. Then pure white, searching for any pixel that fails to light up. On a 100-inch OLED panel, there are over 33 million subpixels. Everyone is tested. Then comes burn-in. The television joins a row of identical units in a testing rack, each screen cycling through dynamic patterns for hours. Colors rolling like waves, gradients shifting, stress testing every transistor, every organic layer, every connection. The televisions glow together in synchronized patterns, a wall of slowly shifting light that looks like something between art and engineering. After burn-in, the television cools, silent, dark. A temperature probe monitors its return to ambient conditions, and then a final inspection. A quality control technician examines the display from every angle, checks the frame finish, verifies port alignment, runs a microfiber cloth along every edge, feeling for imperfections that instruments might miss. When the technician nods, the television is approved. Now watch how carefully this thing is packaged. A protective blue film is rolled onto the screen surface with a felt applicator. No bubbles, no wrinkles. A stand is assembled from cast aluminum components and mounted to the base. And then the television is lowered into a shipping box that was engineered specifically for this product. Molded foam cradles receive the TV. Corner protectors lock into place. Edge rails, face sheets, accessory boxes. each component nested into its exact position. The box is sealed with industrial tape, reinforced at every edge, fitted with corner protectors. A robotic arm lifts the box onto a wooden pallet. More boxes join it. The loaded pallet spins slowly on a turntable as stretch film wraps around it, layer after layer, until the entire load is secured in a tight, transparent cocoon. A forklift carries the pallet through warehouse aisles, lined with hundreds of identical units, each one containing a television that took weeks to create, that passed through machines worth billions, that carries technology developed over decades. The pallet is loaded into a semi-trailer. Cargo straps ratchet tight. The doors swing closed with a heavy thud. Locking bars drop into place, and the truck pulls away from the dock, carrying its cargo out of the factory and into the world. Inside that factory, the line never stops. Another sheet of glass is already entering the clean room. Another plasma glow is already flickering inside a vacuum chamber. Another panel is being born. 33 million subpixels, $15 billion in infrastructure. Thousands of precision steps, hundreds of machines, dozens of engineers, and all of it, every atom, every nanometer, every torqued screw and sealed gasket, exists for one single purpose. So that when you sit down tonight and press that power button, the screen comes alive with a picture so vivid, so deep, so impossibly real, that for a moment you forget you're looking at glass. You forget there was ever a factory at all.